Hello, ladies and gentlemen. My name is Cyrus. I work for AWS AI Labs, specifically Deep Engine, which is responsible for creating SageMaker, and MXNet, which is a framework. I am from the MXNet part of the family. Have the privilege of presenting to you what MXNet actually is and what it does, together with Jay from Chick-fil-A, that would share real-world insights with you about how they have used SageMaker and MXNet to solve the problem they have. So the next 25 minutes, I would be going through basically MXNet's features and what is it all about, and getting slightly technical about it, not very, just somehow. And then I hand over to Jay. So to basically save some time, let's start. So basically, back in the day, back in, I don't know, early 2000, late 90s, when we were doing neural networks, we really were not making a lot of, we were not very successful, basically, because the computational requirements were so heavy that there was no machine to do that, and we could not distribute our load. That went on for a while until the people figured out that there is a graphic card that every professor's kid was actually playing computer games on, and nobody realized we could actually use that to distribute basically a load. And when we figured that out, things started going a completely different direction. So let's start with what a computational graph is. So when you're trying to compute something, you should be able to parallelize parts of it. So after all, in our brain, we have a very interesting parallel processing computer. So here what we have is something called computational graph. If you look at this, you want to compute basically T, you have to compute U, you have to compute K, and if you come down here, you get to some part that computing Z and computing K, they're actually independent of one another. So if we can build a system that can take a look at our, basically the map of our computation, so all of the millions and millions and millions of floating point operations, whether it's multiplication or addition, or we're trying to calculate gradients, and if we build something that can take a look at the map, can map your computation, and then try to find how much of it can be parallelized, then we should be able to compute things faster. And that's what happened. And that's what gave birth to deep learning frameworks. So what a deep learning framework does is general. This is a symbolic code from MXNet. This is not what you really use it, or how you really use it. You use a much higher level API. But let's take a look at that, because that's closer to what the framework does for you. So it's a few symbolic lines of code. So what you're trying to here, you're trying to create a dense layer and with 64 hidden units, and then you're going to have an activation function of ReLU, and then you're going to have a discrimination layer that it does 10 basically classification for 10 classes, and then you pass that through a softmax that can give you a probability distribution of the end. So when you give that to your engine, the engine next tries to map a computational graph for it and figure out what part of that computational graph is going to be parallelized. And it doesn't assign data to it in the beginning. It assigns data lazily. The binding of data is lazily done later. So like here, when you start binding data, here we have the data being attached to it. Then it starts basically running that computational graph forward and backward path and all of that based on the optimized path it has figured out, and it tries to parallelize the computation as much as it can. Because when you're multiplying two matrices, the vast majority of what you're computing can be done without needing to talk to one another when you do your back propagation. And then when your gradients come back to the server, that's the only place they need to be, that needs to be sequential, not even that. So moving forward, when the data is when you bind data to your model, and then it can throw that parallel processing onto a GPU, a Volta, for instance, and try to millions and millions of cores, and try to maximize parallelism into millions and millions of parallel streams of computation. And that's how a framework can help you achieve deep learning, something we could not do back in early 2000s and late 90s. So why do we use MXNet? There are basically several frameworks out there. Prominent ones are TensorFlow, PyTorch, and MXNet. And what does it that MXNet do, and that is important? First of all, it's got training efficiency. What you see in here, long ago, basically MXNet was built for training efficiency in the first place for efficient parallel processing. So what we have in here, there's a training efficiency of 92% for ResNet 152 over 256 GPUs and 16 machines. So that means if you double your compute power, you gain 184% increase in your performance, which is almost linear. It's near linear. Linear is your ideal, that you want to double your computation in a distributed system, and then you would expect that to become twice as fast. So if 184 is very good, given that you have network latency in here, it's not just in a single machine. You have 16 machines that are talking to one another over basically a network. And now we have to try that again, because now we have introduced these, basically in a couple of months there are new instances coming out with 100 basically gig network between them. So that probably can be even improved further. So what else? Then we created, last year we announced it, and we have added so many features to it. Amazon SageMaker. It's built to give you a secure, zero setup, serverless environment to do distributed training. So, and does take care of so much of the distribution on its own, and it's got fast connections to the S3, and S3 can stream information to your model, and that's how the two of them can be married together very nicely. MXNet, because of its ability to do distributed training, and SageMaker, Amazon SageMaker, to give you the tool set that you need to do that. SageMaker has this capability called streaming. So streaming used to be only for the built-in algorithms. So what you see in here is the data that is coming from PCA algorithm that you see when you use the streaming, how basically job execution time, startup, and basically anything that has to do with data streaming gets faster. Why is it important? Because your bottleneck almost always is I/O, is not compute. It's called feeding the beast. Feeding the GPU is a very difficult task because it's so hungry and it just keeps eating your data, and just giving it enough data to make it work is not very easy. So what you have through streaming, you have a fast basically pipeline of basically pumping data to your framework. And then as of last summer, during the New York Summit, we introduced streaming for custom algorithms, not just the built-in algorithms. You can use the same streaming for your own algorithm, and you can benefit from this fast flow of data and hopefully not be starving your GPU. Secondly, there's a boilerplate code you see here. If you're using the SageMaker Python SDK, and then the code that is here, it detects you have multiple machines, and it just distributes your training. You don't do nothing. You just, when you're starting a training job, you give it, I want 4 machines. And it figures out you have multiples of machines, and then using that in order to distribute your training on a cluster, you basically do nothing. And it's kind of non-trivial to do it on your own, because you have to do a lot of optimization, not because of the number of code, but optimization across the cluster. The way it works in SageMaker is that your data is in a bucket, S3 bucket. Your code is either in a S3 bucket or in some sort of a Git repository or somewhere. So the code and the data is going to be streamed or copied to every machine, and then an ECS cluster is going to be built. The machines inside the cluster would be created. You can decide about how to secure it, how to do encryption, and then the training would be distributed in that cluster. The result here would be put on an S3. That would be your trained model, and then the cluster would be destroyed, and you pay only for the seconds that you use that cluster. So that makes it very efficient for these expensive GPUs under the hood. We added this year also automatic model training some time ago. The first version came out that gives you a Bayesian hyperparameter optimization that is applying machine learning to figure out the best combination of your hyperparameters. So those hours and hours and hours of time that you're tweaking this and tweaking that, because hyperparameters, every time you add a new parameter, you're just adding a degree of freedom, and that means an exponential growth in the number of permutations you can have for your hyperparameters. But using that is going to apply machine learning, a Bayesian model, to figure out what is the best combination of your hyperparameters and gives you the best model from the several trainings it has done. So that's another thing that you can gain when you do your training inside SageMaker. So that was training efficiency. When MXNet was created, and in the early stages as we're developing it further, we were having a very academic outlook in it. And the academic outlook is very much focused on training efficiency. Training is everything. Accuracy is everything. It's not made for real world. It's made for experiment. And then we started talking to customers, people like Chick-fil-A, and they told us we really don't care about training because I'm not going to have a large cluster for most of my use cases. And if you saw Andy's keynote yesterday, there's a very small amount of cost, no matter how much training you do, is going to go to your training, even though it could be significant. There have been cases by optimizing training, we have saved the customer in Japan about 22 million a year. But that, compared to the inference, is just small, right? So then we started thinking about developer productivity and inference. So developer productivity came through Gluon. So look at the history of these frameworks. There used to be the good old time. Theano was the first one in here, then Caffe came out, and then TensorFlow created the first truly industrial-grade framework. Keras made it easy by creating a symbolic high-level API on the top of TensorFlow. MXNet itself was mostly symbolic, except for the ND array. And then Chainer came and created the next very good idea. What if, instead of that difficult symbolic programming that would cause your basically scientists or your developers spend 80–90% of their time blindly trying to debug the code and see what went wrong because they had no insight, because of the lazy binding. You build a computational graph, you throw data at it, and then you know what happens. You just wait. Error spews out. You never know why. Layer 3 to layer 4, shape incorrect. You have no idea. You can't look inside. So Chainer came about and created an imperative programming framework that say, what if we have these nice for loops and, like the things that we had in more traditional imperative form of programming, that we could actually put breakpoints on the code, look inside the values, look inside the variables. Why don't we do that? That was an excellent thing they did. PyTorch picked it up. PyTorch became very successful in the academia because of the ease of programming. But what they lost was the speed that you had in here because there was no lazy binding. 2017, we released Gluon. Gluon has a code similar to PyTorch and Chainer by being imperative, but you just get your network and say hybridize, it turns into this. So you have the speed from MXNet, and then you have the ease of programming from Gluon. So you're combining the best of the two worlds together. So that would be your developer productivity. So it's simple coding in Gluon, it's got imperative structure, and it's got dynamic graphs in a way that it calculates what is the shape is going to be. You don't have to layer statically decide about the shape and just statically put in it here. So much of the time that you were doing on a paper, figuring out what the shape of the next layer would be gone because it's just done on the fly. And it's got the high performance of MXNet. And the code that we have seen before is going to look like this. So I'm creating a sequential or hybrid sequential because I want to hybridize it later. Network, that means I'm stacking layers on the top of one another. Then I'm adding a dense layer, and I have basically the final layer that has 10 classes from a library of basically lots of loss function that we have, because that's a classification I've used, the softmax cross entropy. You can attach that to your network. Then you can randomly initialize, or just different ways of initialization, whether it's random, or you can use all zeros, or a specific number, or you can basically get a tensor of a pre-trained network and just use that as the weights of the new network in the cases of transfer learning. So you can do initialization. Finally, you can give it a optimization. Basically, you tell it what optimizer to use. Here we're saying a stochastic gradient descent with a learning rate of whatever. You could make that a stochastic gradient descent. You could be learning rate. You could give it weight decay. You could give it momentum. You could give it all different sorts of things. Or you could do Atom. You could do RMS prompt. You could do some more algorithms that are used for distributed training, such as Zignum, that is not sending the gradients, the values back. It just communicates the sign, which has the same effect. It's very good when you have a large cluster for training. So, and then you move on to train your network. And that's where the difference happens. Here, I'm just loading my data 1 mini batch at a time. I'm running my forward pass of the network here by output equals net, and I'm passing a mini batch to it. By putting it inside this autograd record, what I'm telling it that as you go, I want attach gradients to you, and I want you to calculate the gradients. By calculating the gradients, then that means when you go to the backward pass, it knows it has to go and basically do the gradient descent stuff, and has to basically, and when you go to forward, when you go step, it just has to go and change your weights. So all of that you're seeing here, you can go and put a breakpoint here, wherever, and you can take a look inside what's going wrong. So that is the productivity for developers we're talking about. It doesn't end here. We just released very recently a few libraries like Gluon CV. You can use it for rapid prototyping of computer vision. It has a model zoo that includes some of the most famous and most popular algorithms. And we have massively trained those, so they actually mostly beat the original paper in terms of performance. And then you can use them for transfer learning. So if you just use that pre-trained equals yes, equals true, then you can use basically transfer learning for your own data sets and for your model, so you don't start from a set of random weights. We have done the same thing for Gluon NLP, for natural language processing, such as translation, such as language modeling, such as embedding. So we have the same sort of toolkit and the libraries for that, so you don't start from scratch. You start from model zoo and just continue on from there. It goes on. We introduced in 2017 also Keras backend. And you see here the benchmarking of Keras as you're getting more distributed here over basically more GPUs. From here, from 764 to 1068, you can see that here as well. So MXNet continues improving while TensorFlow stops basically going down. It cannot handle that, like it doesn't distribute as well. This was done before we made improvements to TensorFlow. I'm hoping TensorFlow is not doing that anymore. But we have a team that works on TensorFlow's distribution. So we have done some improvements in there. So it might have changed. But when this benchmark was done, it was before those improvements to TensorFlow. So as you see, by just changing your backend, you gain, without touching your previous code, if you're a Keras shop, you just change the backend of Keras, and that's all you need to do to gain performance, hopefully. There is also Sockeye, something that we released 2016 based on symbolic MXNet. It's a sequence-to-sequence model for natural language, for neural machine translation, and we have made it open. It's basically we made it open source. It was developed by a few guys in Berlin. That's where I'm based, and then Sockeye is pretty much the thing behind all the translation we do these days in Amazon and in AWS. So this is something open source. You can just use it for your own benefit. It doesn't end there. I will have to add a slide in here because MXNet is polyglot. It doesn't have to be Python. We have our API, we have a Scala API, we have Java API. I think we have Perl, I'm not sure. But so the language, we give you the language of choice. You don't have to be chained to Python if you want to use it. Just use Java. So, developer efficiency, training efficiency. Now the final thing is inference efficiency. Things that we heard from the likes of Jay, that really most of my money goes into my inference. Why are you just keep telling me about the training? Actually, that conversation did literally happen when we were preparing for that session. I said, you keep talking about, and then I realized about training, then I realized maybe we have done so much work, maybe we should talk about that too. Recently, we introduced TensorRT. You can see, if you use TensorRT, how you can get faster on the same hardware. So, for instance, ResNet 101, which is the best results we got, using TensorRT becomes twice as fast. So, it's a more recent release on the inference side. The other thing we introduced is NNYM. So these days, the case that you would see soon, you might want to run different inference endpoints. You might be on Raspberry Pi, you might be on Atom, you might be on GPU, you might be on CPU. Then you shouldn't be forced to sit down and optimize your model per hardware, because you have to optimize your model for the hardware you're using. We created something called model compiler. It's going to be called Neo, it's NNVM, whatever you're going to call it. But it's a model compiler. You tell it what hardware you have, and we optimize it for you. You don't have to do anything. There's a couple of lines of code that's saying, I'm going to compile that model for Raspberry Pi, or I'm going to compile that for a Volta GPU, or I'm going to have it on a CPU, Intel CPU. So that hugely helps you for having your efficient inference at your endpoints, and that is done through a model compiler. The other thing is portability. So portability is achieved through two separate things. One is NNVM, so it's a hardware portability. I just talked about that. So you have an abstraction layer, and that abstraction layer helps you to deploy your model in the different hardware. As well as you have ONNX. So you're a PyTorch shop. Excellent. Please don't change your framework. Continue developing your code in PyTorch. Those of us who actually support ONNX, we have basically models can be imported from, model developed by PyTorch. You can import it to MXNet. You can pass it on to the model compiler. So there is you can move from wherever you start and you can go wherever you want to go. So you have the ease of PyTorch. You have an in-house developer team. You have 200 developers that are comfortable with PyTorch. That is too costly to try to convert them to a new framework, and you shouldn't be doing that. But you should be able to have fast and efficient inference. So that means you can import your models to MXNet from PyTorch or from Chainer or whoever else that is supporting ONNX and reap the rewards of basically fast inference. So now there is another problem. So coding is good, research is good, development is good, but that thing needs to go into an industrial grade, into a pipeline of deployment. So you can use Amazon SageMaker for that pipeline. It's a pure DevOps environment for machine learning. So what you do, you can have A/B testing, you can have blue-green deployment, you can have different profiles and decide what percentage goes where. And these are just a few configuration items from the GUI or in your code. You really don't have to do much. So you can now have an end-to-end, basically, environment, a complete end-to-end environment that not only lets you do rapid prototyping, fast inference, but you can also control your deployment, something that has been important for customers like Chick-fil-A to be able to control your deployment environment to thousands of locations if you would like to do that. To recap, you can have MXNet for efficient training and inference. You have Gluon for developer productivity, portability, and you have Amazon SageMaker for an end-to-end platform that is completely serverless and removes the need for you to be building a Dockerized environment and having a load balancer and an auto-scaling group. Just one line of code that you say deploy does that all for you. One single line of code does produce your inference environment for you with auto-scaling groups, with like elastic load balancer. And as the load goes up, you have more machines. As the load goes down, you have fewer machines. And now adding to that the elastic inference that we just introduced yesterday, that you don't even have to have these beefy P2s and P3s for inference. So to give you an idea about how it works, P3 is the cheapest inference if you have 200 requests per second. Sorry, 200,000. If you have 200,000 requests per second, then P3 is the cheapest. But how many of us have 200,000 requests per second? And this is something that we're trying to introduce through elastic inference. That means you have all the goodies of GPU inference, while you don't have to run a GPU machine, a big beefy GPU machine underground in order to be able to have that inference. So with that, I'm going to pass the torch on to Jay, and that would be his comment. So,
thank you, Cyrus. Again, my name is Jay Duff, and I have an awesome role at an incredible company in that I lead a technology innovation center for Chick-fil-A, and we're located on the Georgia Tech campus in Atlanta, Georgia. Last year when I came to reInvent, I had no experience with deep learning or computer vision. I kind of felt like you needed a PhD to do that type of work. I felt like it was over my head, but I did have one of those deep lens devices, and I was really anxious to learn how to use that deep lens device and how we might use it at Chick-fil-A. What I'm going to share with you in the remaining 20 minutes is how we got started with MXNet and how SageMaker helped us with that. So innovation at Chick-fil-A, that's a key part of who we are. We have a rich history of innovation. And in fact, I think you'd be surprised at how much technology is involved in providing a remarkable experience around a great chicken sandwich. In fact, my technology center is only a small part of the innovation that goes on at Chick-fil-A. And one of the things that makes us unique is the fact that we are staffed 100% with students. So it's very relevant to this session about how to get started with MXNet, that what I'm going to show you is all of the work that we did in this past 12 months was done with Georgia Tech students, specifically with 2 sophomores and 1 junior. And among those 3 students, 2 of them had 1 semester of Python. They had no experience with deep learning or computer vision, nor did they have any experience with AWS. So truly, we started from a ground zero when we went into this, and I can assure you that there were no PhDs involved in the testing of these models. The challenge for us was how to get started with computer vision. Our real goal was simply to learn computer vision and to learn deep neural networks. To make sure that it was relevant, our use case relates to waffle fries. So waffle fries are the single largest selling item at Chick-fil-A, as you might expect. And our particular use case was to identify waffle fries that have exceeded their hold time in a product chute. So what that might look like, this is actually an image from the proposed solution at the end. And what you see here is that's an actual product chute. It's a stainless steel chute that the fries would sit in once they were prepared. And the idea was to be able to identify what packages of fries have been in there longer than the hold time. When fries have been held beyond the hold time, they're not optimal. We don't want to serve them to guests. So we wanted a flexible means of being able to identify which ones had been there too long. So if you went to any typical Chick-fil-A restaurant, you would see the fry station. This is a picture taken at my local Chick-fil-A, just looking across the counter. And the fry station is inside that big yellow box. There's a couple of other complexities in this project that came up that we needed to address. First of all, we have nearly 2,400 restaurants, so whatever we developed needed to be something that we could potentially, if we pursued this idea, that we could deploy this across the entire chain. How would you deploy models out to restaurants remotely without ever having gone there? And a couple of other added gotchas here is there's a heated hood over top of the fries. In fact, this is extremely hot to the point that I'm sure it would melt a camera. So you can't put the camera over top of the fries, and you're going to see in a few minutes that would have made life a lot simpler because it would have eliminated occlusion, which I'll talk about in just a minute. Likewise, generally speaking, it's a hostile environment. So you can't just slap a computer on the side of this fry station. I'm sure it wouldn't last much more than a week. So let me talk briefly about how we designed the software and the type of problem that we were going to, or the solution we were going to use to track these fries. This is a solution where we're combining object detection with object tracking. So for object detection, we're using a single shot detection model, and Cyrus mentioned using a model zoo. That simply means there's a bunch of pre-trained models in a library, and we pulled a VGG16 model out of that library. It's a very standard model, and we use, again, a single shot detection model will identify all of the fries in the image, and it will return the location of those fries. So you're going to see that in just a minute, that there might be an image with, say, 10 or 12 fry packages in it, and it will give us the coordinates. It will draw a box around every one of those fries, and we take the location of the fries and we pass that to an object tracker that's in OpenCV. So again, this is a combination of an MXNet model for detecting the fries, but we use OpenCV to actually track the fries as they pass through this particular chute. The other thing I wanted to say here is that we also track hands. Our fries don't normally move on their own, so we know that in the model of tracking, we know that events are only occurring when there's a hand in the picture, in the image. Somebody's putting fries on or they're taking them off. And the other thing you're going to see here in this simple diagram is that we have an error detection loop here. So what's going on here is we take the video and we're going to look at a segment of 10 images from the video. In the first frame, if you will, we take the frame, the image, and we send it to the image detection, or rather the object detection algorithm. It returns the location of the fries, and then in the next 9 frames, we track them with OpenCV. When we've reached the 11th frame, we repeat. And in repeating, we do another object detection, and we resolve the differences between what has been detected with what has been tracked. Because ultimately, as you track things, the tracking isn't perfect, and we need to get things lined back up. So we have a manual, it's the box that says resolve. We resolve the differences between detection and tracking. And I also want to point out, that's the single largest weakness in this design, the fact that we had to resolve those errors manually. But generally speaking, it's a pretty simple program. It's only 1 or 2 pages of Python code. So I want to talk about why use SageMaker. When you get started with deep learning, you're going to find that it's kind of difficult just to manage the development environment. SageMaker is going to support a lot of different frameworks. It's going to support, as Cyrus mentioned, it's going to support MXNet or PyTorch or TensorFlow and others. But underneath each one of those frameworks is a number of other libraries, whether that's the CUDA libraries for the GPU, or it's NumPy, or a bunch of linear algebra libraries. That becomes complex and cumbersome to manage those environments and that software. SageMaker, on the other hand, is completely managed. So if you select SageMaker and you crank up a notebook, you can do that in about 2 minutes, and immediately you'll have a development environment that's ready to go, regardless of which one of those frameworks you're going to use. Likewise, it's going to give you an interactive Jupyter notebook to work with. So if you've never used a Jupyter notebook, that means that you're going to be able to code, write your program interactively, and you can do that from a web browser. So that's very easy. I know in my environment, that also helps me to bypass a bunch of hassles related to security and SSH tunnels and things like that. Being able to do it from the browser was infinitely simple. And remember, I'm working with sophomores and juniors, so simple is definitely good in this case. Likewise, when you get to the point of training, SageMaker is going to make it easy to connect with S3. Undoubtedly, your training data is going to be on S3. And as Cyrus had mentioned, once you start to train and you want to ramp up to more resources, changing to a larger server or more nodes in a cluster is merely a parameter change. So it makes it much easier there. And again, Cyrus also mentioned that when you get to deployment, it's only 1 line of code to take a working model and then deploy it out to EC2. So SageMaker definitely makes this much, much easier, and definitely a good place to get started. The other thing I wanted to mention on this slide is on the right side, you see two general architectures. And we designed the solution to do the inference at the edge. That's the top image there. And specifically, what we wanted to do is put the model to a Jetson TX2. If you're not familiar with a Jetson, it's really a very interesting device, and that has an ARM processor and it has an NVIDIA GPU all on a single board. And our idea was to use the Jetson as a green grass core, and we can deploy the model to that device and then do all the computations on the edge. The second diagram below it, we're beginning to reevaluate this decision. And in the second diagram, that's what our architecture would look like if we do the inference in the cloud. So a couple of points there, that SageMaker is going to easily support either one of these models. It's going to be easy to migrate between the two. And the products that were announced this week actually make both of those solutions a lot easier. Working with the Jetson was kind of difficult, but the compiler that was announced, I think it's called SageMaker Neo, Cyrus referred to it as NNYM. That will make it much easier to take your model and deploy it as a binary to the Jetson, and then you get away from the hassle of managing a bunch of libraries and compiling libraries locally. So Neo would definitely help the top box, and on the second box, the lower one, if you want to do your inferences in the cloud, elastic inference is going to make that much, much more economical and more flexible. But again, my point here was that SageMaker is going to be able to help you either way, and we're kind of working through the debate of whether we should do inference on the edge or if we should do it in the cloud. Why MXNet? I think Cyrus answered a lot of this question. Certainly when we chose MXNet, we were very interested in the performance of MXNet, but we were also interested in MXNet because of AWS's role. AWS is a key contributor to MXNet, and I was confident that there would be good support, and indeed I have had good support from Amazon as we worked with MXNet, as we worked with SageMaker, and in fact we've been involved in a number of the pilots that led up to this week's announcements. If you chose MXNet, how do you go about learning MXNet? You really need to start, I would recommend that you start with a basic understanding of Python. When I started this 12 months ago, I quickly found out that I don't know Python as well as I thought I did. But a basic understanding of Python, you really need to review some basic linear algebra principles, and you need to have a basic understanding of NumPy. And we used OpenCV for managing all of the images as well as the video. And all of these packages are widely adopted. They're easy to use. There's plenty of books and videos and tutorials that you'll find online with examples. So you won't have any problems with Python or OpenCV. When you start with MXNet, I listed two URLs there. The first one is Zach Chase. He wrote a tutorial, MXNet the Straight Dope. That is a really fantastic tutorial. It assumes that you have no prior experience with machine learning. It's going to walk you through the basics of some of the linear algebra. It's going to bring back some calculus nightmares for you that are pretty brief, but it's going to give you a great introduction into deep learning, and it will get you to a point, frankly, I want to go back to what Cyrus was talking about. If you didn't understand what Cyrus was talking about 15 minutes ago when he had the code, by the time you go through these two tutorials, you'll have a clear understanding of what Cyrus was talking about with the symbolic programming and how to debug and things like that. So the second one there is a Gluon CV tutorial. You can take a note of those or simply Google Gluon and tutorials, and surely you'll find these. They'll be the two first hits that you find. But the tutorials were excellent material for getting started with MXNet. As you get started with MXNet and you start to learn and you go through these tutorials, you're going to see that you really have two choices for a development environment. As I mentioned earlier, you're going to have SageMaker, but you might also encounter people that are going to recommend that you use the deep learning AMI. And I would recommend that you start with SageMaker, because clearly you're going to want to use SageMaker to manage the entire cycle of developing, training, and deploying a model. No question, you're going to want it to be familiar with SageMaker. But you might find yourself in a situation where your use case is a little more complex and you need access to the underlying EC2 instance. If that's the case, know that you can use the AMI, the DL, Deep Learning AMI, and that's a good alternative. So in my example, in the work that we were doing, I needed to get access to the Ubuntu desktop, particularly as it relates to doing some of the OpenCV functionality where I wanted to manipulate images. That wasn't easy to do from a Jupyter notebook. So I went back to the AMI during a development cycle, used VNC server to connect, did all of the OpenCV, had a model that was working, and then immediately went back to SageMaker. Again, my point here is to know that both are available. SageMaker is going to be easier to use, but if you run into a situation where you need to get to the underlying machine, or you have issues with versions, for example, you can always fall back to the deep learning AMI. The other thing I wanted to point out here is, it looks like some of my formatting didn't carry through. In our Innovation Center, we work with all students, and it's a bring your own device environment. So we don't give the students any hardware. They show up with whatever laptop they use for school, and we use workspaces, Amazon workspaces, for all of our work. And in particular, that has worked extremely well, and I particularly have enjoyed working with the Linux workspaces that became available, I think, about mid-year this past year. So once you get started with this, you're going to find that training data is paramount. It's extremely important, and it's probably going to be the bulk of your work. What you see here, and the other thing I wanted to mention here before I go into this, is that when you do the training, training becomes a pun here, so let me change my words. When you learn how to use MXNet, the books are going to use public data sets, and you're going to find a lot of helper functions, and a lot of things are going to be automated for you to make it really easy, such that when you go to use your own data, now you're going to have to do that from scratch, and you got to work through the fact that they took shortcuts. So you got to learn this stuff yourself. And again, that working with training data took a lot of time. When we started out, I tried doing the training data manually, and within an hour, you'll figure out that that's a really dumb idea. You definitely don't want to generate training data manually. You'll never come up with 10,000 images in any reasonable amount of time. You're quickly going to see that you need to come up with some way to automatically, in an automated function, generate data. So what you see here in the top image it's two of the students. What they're using is a cell phone, and they're taking a video of the waffle fries on a green screen. And you can see my green screen is nothing more than green construction paper, but it worked really, really well in that by taking a video and then taking the video and splitting it into images, we were able to have a wide variety of images of waffle fries, and they were all labeled. And when I say labeled, to train a detection model, you have to draw a box around every package of waffle fries. And again, you would never want to do that manually. But in this approach, I was able to do it automatically because of the green screen behind it. It was pretty easy functions using OpenCV. And then we used all of that data. We were able to generate 25,000 generally random images, as you see the second image there. 25,000 images was sufficient to get a basic model working. And then we had an iterative approach. And again, I think this is the right way to do it as well. And that we had a basic model, and then we would begin putting real-world videos into the model, and we would go back and then score the inferences. So we might put a video in which might generate 1,000 inferences. We would go through and say which ones were right, which ones were wrong. Of the ones that were wrong, we would correct a portion of those. Then we would take all of that data and feed it back in as additional training data and train once again. So that way, again, it's a means of getting to more complex data, a more robust model without generating a bunch of data and labeling data manually. And again, what I want to mention here is that one of the new products that was released this week, SageMaker Ground Truth, is a great way of managing that iteration. So with Ground Truth that was announced, you can easily put your data into Ground Truth, and you can create a job to recategorize the data, again, to be correct or wrong, and then that will generate another manifest or a list of images, and from that, it's easy to manage how you're going to go back and correct, and then it's easy to take that data and once again, put it back in as training data so that you're iterating. In this case, we iterated about 4 times, and then we had a model that actually performed very well. So let me show you an example of our model. I'm going to show you a video here. One of the things that's funny about the fries is we would go to the Chick-fil-A and we would buy like $50 worth of fries at a time to generate these videos. And after you did this a few times, the fries would be like 2 hours old. And yeah, I wasn't dying to eat fries at that point. Right. Okay, well, let me show you this video here. So what you're going to see is I want to make a couple of comments. One is that the box that we're drawing around the fries, that box is being generated by our program, which is the output of the OpenCV tracker. That's not the box that's related to the single shot detection model, okay? So as we put fries on this, this tray, the model works flawlessly while there's no occlusion. Occlusion simply means that one object is blocking the view of another object. So in this point in the video, that's the first instance of occlusion. And it works okay with occlusion, but there, if you're looking carefully, we're starting to get a couple errors that are related to the occlusion. Obviously, this video is sped up, but you get to a point, it works pretty well, but the occlusion does give it some problems, and our model even works with McDonald's fries, if you look at that. But at some point, it gets kind of confused with the occlusion. Here's another example. And if you watch here in the lower left corner, this is a classic example where we get occlusion between these 2 packages of medium fries, that the 2 packages right there go from 2 to 1. And then when you begin to track from that, that's a good example of the type of tracking error we get because of the occlusion error. And then if you look on the right, you can see red boxes are beginning to appear, and the red boxes are all related to the fact that those fries have been in that chute for more than the recommended hold time.
Oh, so you're not learning whether the fries are good or bad by the way they look. You're just learning that they're bad because they've been on that tray too long.
That's exactly right. So we know that if fries are held, we call it the hold time. If they've been there too long, then the texture is not optimal. So this is clearly an optical or a vision application. And by the way, I want to go back to the comment I made earlier that the goal was to learn deep learning and computer vision. There are better ways to solve this problem, by the way. So that wasn't really the main intent, but we did want to understand how to apply deep learning in the restaurant environment. So a couple of lessons. First of all, training data was hugely important, and we spent the majority of our time on training data and model administration. So how are you going to take these models and deploy them across a chain of restaurants? That would be a challenge, but using Greengrass and using SageMaker certainly would make that possible. But again, that's where the majority of your time would be spent. The other thing is the restaurant use case is, I wanted to emphasize there that not every problem is a software problem. So as we got into this project, we could quickly see that packaging changes of the fries would make this a lot easier. And another thing that we learned was what happens if Chick-fil-A changes the package? Would you have to go back and retrain the model? The answer to that is yes, likely you would. So that was another reason that automating the training data was so important. That in the event, in fact, I think Chick-fil-A, I'm not sure I can say publicly, but I think there are some changes in store for the packaging of waffle fries. Again, you wouldn't want to be in a situation where it took you 6 months to go back and retrain all these models. So packaging was clearly important. Camera placement was important. If we would have been able to put the camera over top of the fries, that would have eliminated the occlusion problem. At this point, we don't know how to do that, because of the heater. The other thing I wanted to mention was the edge compute resources. So We designed this for an NVIDIA Jetson, as I said earlier, because we wanted a GPU. What we found that is performance is hugely important. In the video that I showed you, that video, and again, you saw a video that was sped up, but if I was to show you the actual video, it was running at about 20 frames per second, which was difficult for the way that we had optimized the models. In other words, we took the model and we tried running it on I used an upsquared, a basic Intel chip computer, and that created maybe 1 to 3 frames per second. And then when we went to, we tried a NUC, and I think we got about 5 frames per second. We needed a GPU, a computer with a GPU to get up to 10 to 20 frames a second. So clearly the GPU is very important to our inference speed. There were also some challenges there related to the use of MXNet versus OpenCV. So the truth is MXNet was working really well, and MXNet did in fact use the GPU, but we still had some unresolved issues with OpenCV. OpenCV did not seem to use the GPU. But again, those are some of the complexities you're going to get into when you start working on compute resources on the edge and trying to figure out these libraries, as I mentioned earlier. The other thing I kind of glossed over was the different types of cameras. We have a hostile environment, and what we learned was that we needed to use a USB camera so that we could take the compute device and have it a significant distance from the actual camera location. And you run into some limitations with USB cameras. They're going to be a little bit slower. A reasonably priced USB camera is only going to be good for, say, 30 frames per second, which again was fine in our use case. But if you needed 60 frames per second, a USB camera is going to be expensive, and there's going to be a lot of overhead with serializing and deserializing the data. Again, one of the other things I wanted to come back to is the fact that our algorithm required an error resolution step, and we coded that manually. And in hindsight, I'd say that was terrible. That generally, I think a better design, better leveraging machine learning would eliminate the manual coding. That manual error resolution step just seems to be brittle, and I'm confident that a better design with more complex machine learning would have been a much more flexible algorithm. But overall, we would definitely consider that it was a successful project. Again, we said our original objective was to understand computer vision, deep learning, how we might roll that out across the chain, and I think we did achieve a good understanding of that. And it really brought us to a point where we understand how we might apply computer vision in a few other opportunities or other areas of our business. And so we have 3 projects underway that came out of this project. The first one is a higher performance of object tracking, again, something that uses more complex RNNs or LSTMs to try and eliminate that error resolution step. The second one is one I'm particularly interested in. You see the image at the top is we're using 3-dimensional cameras, and we can look at a human body and translate the human body into 3-dimensional points in space. So if we have 19 joints of your body position, and then we can stream those 19 points into a neural network, and then I can infer your activity. I can infer what you're doing. If I can infer what you're doing, we see that there's applications for compliance monitoring, simple things like, did you wash your hands? How long did you wash your hands? Did you change your gloves after you handled raw chicken? Things like that. That's hugely beneficial to a restaurant like Chick-fil-A. So that's a really exciting application that we're working on now. And finally, we're working on integrating some of this AI capability in with augmented reality. So we're using AWS Sumerian, and we're integrating facial recognition into that, along with object detection and a few other AI types of technologies. We think that a more contextually aware interaction with augmented reality has a very good place in the restaurant business. So thank you for attending today. Thank you for your attention. I hope this left you with an impression that you don't need a PhD to get started with deep learning. And certainly, I would strongly recommend you would want to get started with with AWS SageMaker. It's definitely going to make it easier, whether you choose MXNet or some other framework. That's definitely the right place to start. So we're going to be around here for a few more minutes. I think we can take a couple questions. And I have a few gift cards that will get you a free Chick-fil-A sandwich or a breakfast. So if you come up and introduce yourselves afterwards, I'm happy to share one of those. And if you give us a positive evaluation, I may even give you 2. So do we have any questions?
Can you elaborate how you were able to use a video of that one picture to generate your 25,000 training data points?
Sure. We used a phone just like the one that you have in your hand, and like let's say this is the fries. So we took the video with the camera and merely went at different angles because you want pictures of fries from different angles, okay. All types of different angles. And then if you use OpenCV, you take the video into OpenCV. OpenCV will iterate over the video and will hand you back images, and then you can operate on each one of those images. Now, you need a good random distribution of fries, so you've got to do that over multiple packages of fries, which kind of goes back to the other story. We would walk down to Chick-fil-A, buy $50 worth of fries, and I had a lot of student labor, remember? So I'd put fries in a package, I'd do a video, dump those out, put another one up, do a video. That's exactly what we did. So
makes sense.
In all, we had probably 2 or 3 hours worth of video, and then we would just cycle through it, and it would do all the labeling, and it would substitute the backgrounds.
Thanks.
The question was, did you try the top motion just to see? And the answer is no, we didn't. We knew that would have a huge impact, but I didn't try that. Sure.
I work for Liberty Mutual, and so we're very interested in watching the body joints and safety for workers' comp and other things like that. But on the camera, did you guys consider maybe a mirror might give you an angle of seeing the fries without placing the camera there? And then a deeper follow-up would be, you basically talked about this as a training use case, not necessarily optimized to the business operation.
That's right.
Could you talk about how you're thinking about optimizing, where you see direct applications, maybe like what you were talking about with the body joint tracking and so forth, but other things that you've thought about in the business where you see a more direct application and less just the learning cycle?
Okay, well, your second question actually answered the first one in the sense that I'm more of a research and development organization, and again, I want to emphasize that I have sophomores and juniors programming this, so by no means is their code ready for production. That said, they're pretty good at developing conceptual ideas and prototypes. So my role or my innovation center will take a concept like this, develop a prototype, show it to the business, and then go to the business and say, hey, are you interested in pursuing this, and do you want to take it further? This, I believe, has been taken to a point that if the business wants to take it further, it probably won't involve me. We would probably go to an outside firm. We would probably go to an equipment manufacturer and say, hey, this is generally what we want you to do, and let them solve the camera issue. So that kind of goes back to your other question too about that really wasn't our goal, and I only take it so far. But we did prove that computer vision would be a good way of solving this problem. Then your other question about other areas that we're looking to apply that, I think I'm having a more difficult time answering that question, other than to say that we at Chick-fil-A, it's a very well-run company, it's very well aligned, and for example, we know that food safety is very important, and that's where we've been able to see that, hey, being able to solve food safety or improve food safety has huge benefits. And what was interesting in the food safety project, if I can just digress for a second, was we actually had another project I'm not talking about, but it was to make a dancing cow, a Chick-fil-A cow, that we wanted kids in a restaurant to be able to make a cow dance. But then we quickly realized that, hey, that same technology would be applicable to food safety. So we kind of made a pivot from, say, a Microsoft Connect over to Intel RealSense and using more complex models to do that. So that's really where we're just prototyping with and exploring multiple technologies, knowing what's important to the business. That's how we got to these other ideas. Oh, I'm sorry.
You mentioned you had some problems with OpenCV. If you were to do the project again, knowing all that you know now, would you still use OpenCV, or is there another library that you'd recommend?
That's a good question also. Amazon provided me with a lot of really good support in this project, and they did tell me that there were some other better trackers than using OpenCV. But I got to the point where, hey, I just wanted to do a prototype. I know there's a better solution. And right now, one of the projects we're working on is actually we're using a shell game idea to try and do some more sophisticated tracking. And there we want to get away from OpenCV.
So there are a couple of things you want to consider here, Mo. We have built Gluon CV on the top of OpenCV. Some of the data augmentation features that you have in OpenCV do exist in Gluon CV, and hopefully they would not have the same problems. So if you really want to do some sort of data augmentation and building a pipeline for data, look at the Gluon CV's utils library, the APIs that are in the utils.
Great, thank you.
Cheers.
Thank you, Cyrus.
I understand that Chick-fil-A is using edge hardware in the restaurants for IoT use cases within the kitchen. Is there any interest in leveraging that kind of hardware for your imaging case?
I'm sorry, what was the last part of your question? Leveraging it for what?
For this use case of computer vision.
Again, it kind of goes back to the earlier question. You are correct that we are using, we do have a rather sophisticated approach to IoT in the restaurant. It involves Kubernetes, and it's not really positioned well at the moment to have a device that has a GPU. So we can use Greengrass in the same restaurant. It could definitely work on the same network, but we haven't solved the issue of how do I get a GPU device. It's not part of the existing stack, but that would be a part of when we take this from a conceptual idea to an actual implementation. That would be one of the things we would have to solve.
Thank you very much.
This question will be pretty easy for you. The co-location or the location near Georgia Tech University using students to develop this prototype, brilliant. So two questions. How many students were involved in this initial exploration and development of the prototype? And then what were their majors? Were they more computer science? Were they from the business school? Or was it just a big diverse group?
That's a good question also. Our innovation center has been operational for about a year, and a lot has changed. So my answer isn't going to be, you can't infer too much from my answer. So the first part of your answer is we had 3 students, and they spanned, I had 2 working on it in the spring and 1 in the summer, and they were all computer science majors. Since then, I have used students from other schools, so I'm getting better results on innovation projects when I have a more diverse student body. So now I have 5 or 6 schools making up the students in the Innovation Center. When I did this project, they were exclusively Georgia Tech. So that's the first point. The second point really kind of goes back to what Cyrus was saying, is that much of the work that we did here was difficult in the sense that MXNet and Gluon was progressing and improving rapidly. So I began this work last December, and MXNet was on version 1.1. Then we got to Gluon, and I had it almost working with Gluon, and then Gluon CV came out, and then they went to 1.3. My point of that is that the software libraries were changing rapidly, and it was getting easier and easier. So what took me 6 months, had I had Gluon CV at the beginning, I probably could have done it in 3 months. But earlier in the year when Gluon CV hadn't been released, I was kind of struggling with a few things.
Thank you.
Any other questions? All right, well, again, thanks for the great questions too.